Kavitha, Assistant Professor, Department of Mathematics, Dr. SNS Rajalakshmi College of Arts and Science. Today's topic is mathematical formulation of LPP. How to formulate the LPP as a mathematical structure. First of all, the linear programming problems, the key components are decision variables. These represents the choices available to the decision maker, and the objective function, a mathematical function that needs to be maximized or minimized, and it has a constraints, a set of linear inequalities or equations that limit the feasible solutions, and non-negativity restrictions. The decision variables must be non-negative. Mathematical formulation of LPP, the structure of the LPP is objective function that is maximized or minimized, and the next is subject to constraints, and then on non-negativity constraints. Now we go on to the mathematical formulation of LPP. First, step 1, we take the decision variables. Step 1, define the decision variables x1, x2, x3, etc. xn. Next, step 2, construct the objective function which has to be optimized as a linear equation involving decision variables. Next, step 3, express every condition as a linear inequality involving decision variables. Step 4, state the non-negativity condition and hence express the given problem as mathematical model. This is the mathematical form of LPP. We take the decision variables as x1, x2, etc. xn. The mathematical formulation, first one, find the values of x1, x2, etc. xn which optimize the linear function, that z is equal to this is the format for the objective function, c1 x1 plus c2 x2 plus etc. plus cn xn. The next equation is subject to the constraints. It involves all the feasible constraints. Here a11 x1 a11 x1 plus a12 x2 plus etc. plus a1 and xn. This is less than or equal to or greater than or equal to b1. The third equation is non-negativity restrictions, that is x1 comma x2 etc. xn greater than or equal to 0, where all c's, b's and a's are unknown constants. Here the equation 1 is the objective function, equations 2 are called constraint, and equation 3 is non-negativity restrictions. In equations 2, less than or equal to, greater than or equal to means that any one of these signs three signs may be there. This is the example formulation of LPP. Here we take a problem, diet problem. A person wants to decide the constitution of a diet which will fulfill his daily requirements of proteins, carbohydrates as the minimum cost. The choice is to be made from 4 different types of foods. The yield per unit of these foods are given in the following table. That is food type. There are 4 types are given, 1, 2, 3, 4, and the yield per unit given by the nutrients, proteins, fats, carbohydrates, and also give the cost per unit. Food type 1 45, food type 2 40, food type 3 85, and food type 4 65. Minimum requirement for protein 800 and fat 200, carbohydrate 700. Here the formula, here the problem is formulate a linear programming model for the problem. Just we convert the problem to the mathematical model. First, let the number of units of food types 1, 2, 3 and B represented by x1, x2, x3 and x4 respectively. This is the decision variables. We take the first step 1, take the decision variables. The decision variables as x1, x2, x3, x4. We take the decision variables as food types. And also the cost per unit for food type 1 is given by 45, food type 2 is given by 40, and food type 3 is given by 85 rupees, and food type 4 is given by 65 rupees. So the total cost we have to convert it is a function, that is z is equal to 45x1 plus 40x2 plus 85x3 plus 65x4. Now the objective is to minimize the cost. So the objective function will be minimize z is equal to 45x1 plus 40x2 plus 85x3 plus 65x4. And also since the number of units of food types cannot be negative, so x1 greater than or equal to 0, x2 greater than or equal to 0, and x3 greater than or equal to 0, and also x4 greater than or equal to 0. This is the non-negativity restriction. Then we have to find the constraints. Constraints are the fulfillments of the daily protein, fat and carbohydrate requirements. Here the problem given by minimum requirements. This daily requirement of proteins is at least 800 units. At least 800 units. So by the above table, we convert this as an equation, that is 3x1 plus 4x2 plus 8x3 plus 6x4 greater than or equal to 800. And also his daily requirement of fats is at least 200 units. So by the above table, 2x1 plus 2x2 plus 7x3 plus 5x4 greater than or equal to 200. And the same, his daily requirement of carbohydrate is at least 700 units. So by the available table, 6x1 plus 4x2 plus 7x3 plus 4x4 greater than or equal to 700. Now the mathematical formulation of LPP as the given problem. This is the inequalities. The system of inequalities is called the constraints, subject to constraint. Now, hence the linear programming model for this given problem is minimize z is equal to 45x1 plus 40x2 plus 85x3 plus 65x4 subject to 3x1 plus 4x2 plus 8x3 plus 6x4 greater than or equal to 800. 2x1 plus 2x2 plus 7x3 plus 5x4 greater than or equal to 200. 6x1 plus 4x2 plus 7x3 plus 4x4 greater than or equal to 700. And x1, x2, x3, x4 greater than or equal to 0. This is the mathematical formulation of LPP. Thank you.